Sound. The nature of sound. Its properties. Infrasonic. Ultrasonic. Doppler effect. And various technological applications. What causes sound? Every sound is produced by an object that vibrates. Your friends' voices are produced by the vibrations of their vocal cords. Music from a guitar, from vibrating strings. And voices from a loudspeaker, are produced by vibrating speakers. When an object vibrates, it creates kinetic energy that is transmitted by molecules in the medium. As the vibrating sound wave comes in contact, particles passes its kinetic energy to nearby molecules. As these energized molecules energize other molecules that repeat the process. Sound waves are compression waves. The wave energy transfer is compression, nearby molecules are pulled together creating high pressure. And rarefaction, nearby molecules are spread out which gives low pressure. This creates a pressure wave, that causes particles in the surrounding medium to have vibration motion. The matter that a wave travels through is called a medium. The medium can be gas such as air, liquid substances like water, or any solid material, like steel rail. Take note that sound waves cannot travel through vacuum, or empty space. When a radio speaker vibrates outward, molecules are pushed together. When the speaker moves inward, molecules spread out. As long as the speaker continues to vibrate back and forth, compressions and rarefactions are formed. Sound can travel through any kind of matter, but not through a vacuum. The speed of sound is different in different materials. In general, it is slowest in gases, faster in liquids, and fastest in solids. The speed depends somewhat on temperature, especially for gases. The intensity of a wave is the energy transported per unit time across a unit area. The human ear can detect sounds with an intensity as low as 10 to the exponent minus 12 watt per meter squared, and as high as 1 watt per meter squared. This range is equivalent to the sound level, from 0 decibels, the threshold of hearing, to 120 decibels, the threshold of pain. The intensity of sound diminishes with distance. In open areas, intensity is directly proportional to the inverse of square of distance. However, in enclosed spaces this is complicated by reflections. And if sound travels through air, the higher frequencies get preferentially absorbed. Loudness is related to intensity of the sound wave. The loudness of a sound is proportional to the logarithm of the intensity. The sound level can be described using a measurement scale, unit in decibels. On this scale, the faintest sound that most people can hear is 0 decibel. Sounds with intensity levels above 120 decibels may cause pain and permanent hearing loss. What happens to the sound waves from your radio when you adjust the volume? The notes sound the same as when the volume was higher, but something about the sound changes. The difference is that quieter sound waves do not carry as much energy as louder sound waves do. When you turn down the volume of your radio, you reduce the energy carried by the sound waves, so you also reduce their intensity. Pitch is directly related to frequency. It is how high or low a sound seems to be. A high-pitched sound corresponds to a high-frequency sound wave, and a low-pitched sound corresponds to a low-frequency sound wave. Frequency is a measure of how many wavelengths pass a particular point each second. It is measured in hertz. When a sound wave with high frequency hits your ear, the sound has high pitch. As the frequency of a sound wave decreases, the lower the pitch becomes. A healthy human ear can hear sound waves with frequencies from about 20 Hz to 20,000 Hz, upper limit decreases with age. The human ear is most sensitive to sounds in the range of 440 Hz to about 7,000 Hz. Those sounds below 20 Hz are termed infrasonic, while those above 20,000 Hz are ultrasonic. Humans cannot detect infrasonic. Some animals that can communicate using infrasonic sounds are rhinos, hippos, elephants, whales, pigeons, and many others. Certain animals that can emit and hear ultrasonic frequencies are bats, dolphins, insects like beetles, moths, dogs, frogs and toads, and many more. How do we hear sound? Sound waves enter the outer ear, and travel down the ear canal to the eardrum, which vibrates in response. Inside the middle ear, the hammer, anvil, and stirrup transfer vibrations to inner ear, and amplifies the waves. Within the inner ear, cochlea transforms vibration energy to electrical energy, and sends signals to the brain, which turns it into a sound that we recognize and understand. One of the important uses of ultrasonic waves is in medical diagnosis and treatment. Using special instruments, ultrasonic waves are sent into a specific part of a patient's body. Reflected ultrasonic waves are used to detect and monitor conditions, such as pregnancy, certain types of heart disease, and cancer. Infrasonic, or subsonic waves, are produced by sources that vibrate slowly, such as wind, heavy machinery, and earthquakes. Although you can't hear infrasonic waves, you may feel them as a rumble inside your body. Infrasonic sound waves are also used to estimate the size, shape, and depth of underwater objects. Sonar is the system that uses the reflection of underwater sound waves to detect objects. The Doppler effect is the apparent change in pitch, or wave frequency, due to a moving wave source relative to a listener. It occurs, whether it is the sound source, or the observer, that is moving. As the source of sound waves approaches the listener, the sound waves get closer together, increasing their frequency, and the pitch of the sound. The sound wave from siren of a stationary police car are represented as concentric circles, radiating outwards. When the car moves, notice the sound waves in front on the car are getting closer together. Thus, for an observer in front, the effective wavelength is shortened, giving an apparent higher frequency, so a higher pitch can be heard. However, for an observer at the back, the effective wavelength is longer, giving an apparent lower frequency, so a lower pitch can be heard. This phenomenon is known as the Doppler effect. When the wave source is moving towards observer, the wave received are with shorter wavelength and higher frequency. But when the wave source moves away from observer, the sound has longer wavelength and lower frequency. The Doppler effect also occurs in electromagnetic waves, such as radar waves. Its application includes radar guns that measure the speed of cars. Weather radar also uses the Doppler shift to show the movement of winds in storms, such as a tornado. Let's have some problem-solving examples on Doppler effect. A man hears a 450 Hz horn while the fire truck is traveling at 25 meters per second. What is the frequency he hears when the fire truck is approaching, and after it has passed? Here is the formula for frequency when sound source is moving and approaching. Let's substitute the 400 Hz frequency of sound source and its 25 meters per second velocity. Thus, the apparent frequency the man hears is 431 Hz. Here is the formula for frequency after the moving sound source has passed. Again, let's substitute the 400 Hz frequency of sound source and its 25 meters per second velocity. Thus, the apparent frequency the man hears is 373 Hz. Let's have another one. A police car at rest turns on its 1600 Hz siren. What is the frequency you will hear when you are jogging at 5 meters per second towards it, and after you passed it? Here is the formula for frequency when listener is jogging or moving towards the sound source. Let's substitute the 1600 Hz frequency of sound source and the 5 meters per second velocity of a listener. Thus, the apparent frequency the jogging listener will hear is 1623 Hz. Here is the formula for frequency when listener is jogging or moving away, and has passed the sound source. Again, let's substitute the 1600 Hz frequency of sound source, and the 5 meters per second velocity of a listener. In this case, the apparent frequency the jogging listener will hear is 1577 Hz. A train sounds its whistle as it approaches a tunnel in a cliff. The whistle produced a tone of 650 Hz. If the frequency heard in the tunnel is 693 Hz, what is the velocity of the train? Again, here is the formula when sound source is moving and approaching. Let's substitute the 650 Hz frequency of train whistle sound source, and the 693 Hz apparent frequency heard in the tunnel. To solve for the velocity of the train, first we cross-multiply. So, on the left, that's 693, times the quantity 343 minus velocity of source, Vs. On the right, what is left is 650 times 343. Then we distribute. On the left, 693 times 343 is 237,699, minus 693 Vs. On the right it's 222,950. Then we transpose 237,699 from the left to the right. Note, the sign changed to negative. Divide both sides by 693. Thus, the velocity of sound source, or the train, is 21.3 meters per second.